All right. So today, like I said, is all about logistics. Now, a logistic growth function is a function related to the exponential function, not a log function. A logistic is a type of exponential. It has absolutely nothing to do with log. Nothing to do with log. It's an exponential. Why the heck they decided to call it logistic? I don't know, just to confuse us. Now, a logistic function is used when there's a restriction on the growth. So if we think about a normal exponential, what does a normal exponential function look like? A backwards letter what? Letter L with a curve, right? Yeah. So it starts off very, very flat from the left to the right, and then it increases exponentially. A logistic function starts off the same way. It starts increasing, but then at its inflection point, it's called, its change in direction, it kind of peters off. It kind of looks like a cube root, to be honest, with an inflection point, just like a cube root had an inflection point. So there's a restriction on the growth, meaning it doesn't exponentially grow like a normal exponential would. Now there's 3 different forms of this logistic growth function, but the one that we're mainly going to use is this center one right here with a base of E. This is the one we're mainly going to focus on, because this is the most real world applicable of the 3. Okay, so let's look at it. Like I said, a logistic growth function has an inflection point or a point of inflection. It also has 2 asymptotes, one at the bottom and one at the top. Now, looking at this, what is our domain of this logistic growth function? All real numbers. And it will always be all real numbers. And where are our 2 asymptotes? Y equals 0. It'll always be y equals 0. And where else? Y equals c. Now, where did that c come from? I'm looking at my growth function. The numerator. You can always find the top asymptote from the numerator. Now, this c is a very, very special number when dealing with logistic growth functions. It's called the carrying capacity. I believe you've already heard this terminology. I think you heard it in bio before. But basically, when we're thinking of population, which is the most common application of logistics, is populations of animals or humans or whatever, the carrying capacity is the max amount that the population can be. And it's always the numerator of our logistic growth function. It also turns into our top asymptote. And if we know what our C is, we can find the Y value of our point of inflection. What do we do to find the Y value of our point of inflection? What does it say? Yeah, you take your carrying capacity and you divide it by 2. This will give you the Y value of the inflection point. I also want to mention that the B value in this growth function, that B value is your growth factor, it's called. Growth factor. It will always have a negative in front. All right. So let's go ahead and look at C, because I think C is the hardest to think about. So let's look at C to find the domain, range, point of inflection, symmetry, boundedness. Ooh, let me mention boundedness. Because you have two asymptotes, this entire logistic growth function is bounded both above and below. Which asymptote do you think is binding this below? The y equals 0 or the y equals c? Y equals 0 is what is binding it below, or it's called bounded below by y equals 0. And which one do you think is binding it above? Y equals c. So we say it's bounded below by y equals c. I'm sorry, above. Oh God. It's bounded above by y equals c. So I'm looking at this part C. We're trying to find, what does it want first? Our domain and range, I think. What is our domain of this logistic growth function? All real numbers. Wonderful. What about our range? Yes, it goes from 0 to 20 because that's where our what are? Asymptotes. Our asymptotes are at y equals 0 and y equals 20. Now, eventually it does want us to do boundedness. So which one of these asymptotes binds it below? Yep, so we say it's bound below by y equals 0. And which one binds it above? Y equals 20. So we say that it's bound above by y equals 20. All right, what does it want next? So we found domain, we found range. Okay, point of inflection. Inflection point. How do we find the inflection point? Half is C. So our C value is what here? 20. 20 divided by 2 is how much? But what does that give us? Just the y value, but this is a point. So what do we also need? You also need the x value. All right. So either we can take 10, plug it in for f of x, and solve for x using everything that we now know about exponents. Or you can take your calculator, go into y equals, type in our equation, 20 divided by, now everything in the denominator needs to be in parentheses. This is the most common mistake here, is forgetting to put the denominator in parentheses. So we have 1 plus 2 times e, which you just hit second ln to get e. minus 3x. And I look at my graph. Now my graph, I changed a little bit. I changed the window. It originally was, our y was negative 10 to 10. Why did you think I changed that? Couldn't see it. What do you think the top number for our y value should be bigger than? Bigger than 20. Basically, when you're thinking about your window, you should be looking at your domain and range. I need to at least see from 0 to 20 to see this entire thing. So I'm going to do 25. How do you think I can find the point on this graph where y is 10? So if I look at my table, it doesn't get specific enough with my y values to find when y is 10. So that doesn't work. Trace is never going to be accurate enough. Trace is never going to be, I really don't want you ever trying to do trace in here. No, guessing is not good. There is a foolproof way that we can find when y is 10. No one can guess or think or give me, yes, Uma. You could solve algebraically, but that's a lot of work. Yes. Yes, exactly. Go to y equals and type in y2 is 10. Where those two lines intersect is going to be our inflection point. So how do we find intersections on the graph? Second trace, 5. And first curve, the first question it's going to ask is first curve. That just means get it on the first line. It should already be there. Press enter. Second curve means get it on the second line. It shouldn't jump to the second line. You just press enter. And then guess, get right on the inflection point and press enter. And we have the point 0.231, comma 10. Yes. It's because you won't ever have a value here, like moving it up or down. Well, think about it. Y is the population. So can you have a negative population? Mm-hmm. It would in theory, yeah. But that in the real world won't happen. Yeah. All right, so what's next? What are we doing next? Symmetry. Okay. So this is dumb, but symmetry is basically asking for whether this is even or odd, meaning is it symmetric with respect to the origin or y-axis? And remember, y-axis was if it was even, origin was if it was odd. Is this symmetric with the origin or y-axis? Is it? No. In fact, logistics are never going to have any sort of symmetry, so we just say none. Always. Asymptotes we already found. Lastly is end behavior. So our end behavior, as x goes to negative infinity, what does y go to? 0. And as x goes to infinity, what does y go to? 20. Now, just because I think that this pops up on your Math Excel, there's actually another way to describe end behavior. Has anyone heard of the second way? It's actually like a huge concept in calculus. What if I wrote this? What do you think LIM stands for? Limit. Yes, you can describe end behavior as limits instead, which the only thing that's changing is instead of writing as, we're writing LIM, and then where x is approaching goes right below the limit. So what was x approaching at first? Negative infinity. So this reads the limit as x approaches negative infinity is what? What did f of x or y approach? 0. That's how you write a limit. And then we have to state the other end, the limit as x approaches. What did x approach at first? Positive infinity. What did our y value go to? 20. True, but he's asking in general. Yeah, in general, with limits, you would put an arrow infinity because you can never be infinity. I know here you can't technically be the asymptote either, but there would be an arrow. Yes, we're not going to do that in here. It can be. You can have a limit that's infinite. Yes. It's the only way that you're going to, yeah. All right. So now, nope, I'm going to pause.